Hello and welcome to Nature Live Online, the show that takes you behind the scenes at the Natural History Museum, London. From dinosaurs to DNA, from volcanoes to vampire squid, we bring our museum science direct to you at home. Now, today we're finding out what million-year-old fossils can tell us about our climate emergency today. I'm going to be chatting with museum paleontologist Richard Twitchett, who studies how our oceans have responded to climate change in the past. Now, as usual, this is your chance to put your questions to our scientists too. So do pop any comments, any questions you might have in the chat box. We'll do our best to answer as many of your questions as we can. Say hello, tell us where you're watching from. We'd love for you to join in the conversation. But now let's say a very big welcome to our guest today, Richard.
Hi, Alison. Hi, everyone.
Hello, Richard. It's great to have you on the show today. Always lovely to chat to you. I'm going to dive straight in, if I may, because we have so much to get through, so little time, as always. But Richard, as a paleontologist, you study the past, but actually the focus of our chat today is very much on the present and possible future. Currently in Glasgow, world leaders are gathered for COP26 to discuss our response to our climate emergency. What can we do? Just to set the scene a little bit, I wanted to start by taking a look at a now quite famous graphic. Richard, what does this image tell us and why is it important?
Yeah, so Alison, this is the graph that shows us basically the rise of carbon dioxide in the atmosphere. In this case, over the last 60 years or so, from the Mauna Loa Observatory in Hawaii, where they measure on a daily basis how much carbon dioxide is in the atmosphere at that point. So let's go back, sort of from the late 50s there to the present day. We can see the numbers up the side. I won't ask you when you were born, Alison, but but when I was born, CO2 there was around about 325 parts per million in the atmosphere, and you can see at the present day it's over 410. In fact, it's around about 414 actually today, I think. So we've seen this steady rise through time, and of course this is what we're all rightly concerned about: this big greenhouse gas, carbon dioxide, that human activity is contributing to the atmosphere. So yeah, most of the time there you can see it's sort of been in the 300s. Most of my life it's been in the 300s. But the number that I think is really interesting and a sort of milestone that was crossed is that 400 line. So most of us on the planet were born when carbon dioxide levels were in the 300s, but there's a small and growing proportion of humans on the planet who have only breathed air with 400 or more parts per million CO2 in. And as you can see on that curve, CO2 fluctuates a little bit, but it's been consistently and constantly above 400 parts per million since November 2015. So in fact, 6 years. So every single person, I don't know when there are any watching us right now, but every single person who is 6 years old or less has only ever breathed 400 parts per million or more CO2 in their lifetime so far. And because it takes so long for carbon dioxide to come out of the atmosphere once it's in there, even if we stopped all emissions at the end of this week, it would still take many decades and possibly most of their lifetimes for that to drop back down below 400. So it's the numbers, give us these milestones that obviously would, the atmosphere is moving past and through.
And it is a significant milestone, isn't it? If we put it into historical context, am I right in thinking no other human generation has breathed an atmosphere at 400. Is that true?
Absolutely. And this sort of graphic shows that. So here we have now we're looking at a curve of carbon dioxide levels, not back to 1960, but back 5 million years into the past, into the Pliocene, from the present day there. So there's the 400 line that we've just spoken about, and there's the little dot at the end there at the present day. Above that, you can see the little image there represents our species, the lifetime of our species, which is only about 100,000 or 200,000 years. So our species, Homo sapiens, has only been around for that long. And you can see there that in all of that time, literally apart from the last 6 years, CO2 has been a lot less than 400. So the current generation, and in fact all of us on the planet, are breathing more carbon dioxide than any of our ancestors have ever breathed. And that 400 generation are the ones who've never breathed anything less. So then we go back through time. We go back then to say the next bar above there goes back to about 2 million years, and that's representing there all of the closely related species to our species. So these are other species of Homo, including the Neanderthals, for example. And again, none of them ever breathed atmospheres with more than 400 parts per million in at all. You have to go back to that final block there, the Australopithecines, these sort of ancient extinct ancestors of humans living in Africa, so Lucy and her like, in the Pliocene, before you find generations of hominins who were breathing more than 400.
Wow, it's incredible, and it really does help put that whole generation 400 into context. It's quite mind-blowing. I see we've got people watching from the UK, Philippines, Italy, so very big welcome to all of the viewers joining us. All of us now breathing 400 parts per million of carbon dioxide.
Exactly, and that generation, those children born since November 2015 really are special. In this broad, long-term time view of atmospheric CO2.
Now, how do we actually know how much carbon dioxide was in the atmosphere during the Pliocene, or just in the past generally? How do we know that?
Yeah, so it's measured daily. At the moment, we can, with instruments. So if we go back to that plot there, we can see that back through the last sort of probably about to about sort of 750,000 years, 800,000 years, we actually have really long ice cores from Antarctica and Greenland, and in the ice cores that have been extracted, the little bits of the atmosphere are actually trapped as sort of air bubbles, if you like, within the ice. So certainly back to 1 million years, that's a record that we can again directly measure. Beyond that, we're using ways of estimating CO2, and these are called proxies. And sometimes it's chemistry, but also we can get some idea directly from the fossils of the organisms, and in particular the plants that were living at the time. So here on the screen now you have a modern and a fossil ginkgo leaf, and these trees are around at the present day. You've probably got them, some of you out in your local parks, turning nice and yellow in the winter and autumn. And we get the fossils of these plants going back to several hundred million years. And all trees, all plants, what do they want to do? They're photosynthesizing. They need to bring carbon dioxide into their leaves, and they also need to sort of release oxygen again out. And to do this, they have these little pores on the surface of the leaves called stomata. And you can see these. They're if you zoom in at very high resolution under a microscope, you can see these little pores on the surfaces of the leaves. And and these are tightly, the density of those stomata on the leaves is very closely linked to the amount of CO2 in the atmosphere. And the reason for that is that the plant also loses water from these pores, which it doesn't want to do. So when CO2 levels are high, it can have fewer stomata, which means it still has CO2 but doesn't lose as much water. And we can still find those leaf surfaces, those pores, those stomata, preserved in the fossil leaves, and we can measure them, count them, and estimate therefore how much CO2 was in the atmosphere when those fossil plants were actually alive.
That's absolutely brilliant. So that tells us how much CO2 is in the atmosphere, but we know obviously CO2 is a greenhouse gas. It warms our planet. So what evidence can we use to understand what the climate was like during the Pliocene?
Yeah, so here we're sort of maybe interested in something like temperature, and to understand temperature in the past, quite often what we're using are chemical techniques. So we're looking at the chemistry of again either soils perhaps, or animals, the skeletons, the shells, the bones, the teeth of the organisms that were living at the time, and the chemical signature can tell us about the temperatures.
And here we have some of your favorite specimens, I know.
Yeah, I mean, these are the most important marine animals that most of you watching have probably never heard of. This is a brachiopod. It's a sea creature. It has two shells, much like a bivalve, but that's really where the similarities end. These organisms are found in the present-day seas, including around the coast of the UK, although not close to shore, so we don't often see them. And they have a very long evolutionary record going back 500 million years into the Cambrian. And you can see on the surface of that shell there, you can see the little growth lines. As the animal grows, it adds a little bit to its shell, as most sea creatures do. And the chemistry of the shell of these animals is very resistant to fossilization. So it's a type of calcite that still retains the chemical signatures of the seawater in which the animals were actually living when they were alive. And this is an example, this one here, from the Pliocene, from this time, last time that CO2 was as high as it is at the present day. And so we can actually analyze the chemistry of the shells, if you like, to reconstruct the seawater chemistry, including temperature. So that's what we can do, and we do that at the museum. So for instance, for this particular animal, how would we do that? First of all, we could slice the shell in half, and so here we go. Here's a slice through, and you can see the two shells, halves of the shell there, below and above, quite clearly, and it's filled in with the fossil seafloor sediments there. And we can take that slice, that polished slice, and we can put it, in this case, under a laser, and the laser zaps the surface of the shell, releases the chemical elements that are in there, which can then be measured by the machines there. So we can zap that using this really high technology. We can actually see how seawater temperatures fluctuate through the life of that individual animal back in the Pliocene of Suffolk in this case.
That's absolutely amazing. And it really goes to show the value of our historic collections as well. The scientists that collected that brachiopod, for example, would have no idea what it would be used for today.
Exactly. And that particular example was collected in the late 1800s. And of course, it was collected not because somebody thought 100 to 20 years ago, oh, it's going to be used for climate change in the future. No, they collected it because it's a lovely, beautiful example. And it's only with the development of technology, and obviously also because we're interested in climate change, we want to understand the past, that these historic collections now become so valuable. They are archives of climate and environmental information. And some of the sites that these things were collected from are just no longer accessible at the present day. So this really is a valuable resource there.
Absolutely. I want to move on to talk about impacts of climate change in the past. But before we do that, we had a question come in from one of our viewers watching in China, asking, with more carbon dioxide and less jungles to make the soil acidic, could there be an increased number of fossils in our future fossil record?
Oh, that's an interesting one. Yeah. So, the amount of fossils, it really depends on the environment in which the animals died and became preserved. And actually, yes, there's as we'll see in a minute, certainly in the seas, one of the impacts of climate change is to change the environment and actually to make it, although there aren't many animals necessarily living there, what can be living there can actually get preserved better because of the conditions that we find the seas in. So all of these, the environment, climate, fossils, and fossilization is all interlinked.
Fascinating, and it brings us on very nicely to talking about impacts, because we can tell CO2 levels, we can look at temperature, but we can also look to the fossil record to find out about the effects, the impacts of past climate change, can't we?
Yeah, we can. So I mean, quite a lot of people sit there and scientists will make predictions and talk about the future. And if I wanted to do that, I would actually take you, Alison, to see one of these past events firsthand, up close, out in the rocks on the coast, and you can actually see for yourself what the seafloor looked like during one of these past warming events, because the Earth has gone through this many times before. A lot of these big warming events, they're related to times of big extinction or crisis, and of course the Earth system's recovered and then have progressed. So here we have on the screen here, we actually went to one of these events, one of these warming events, which is also one of the big extinctions at the end of the Triassic, about 200 million years ago. This is a piece of the rock record from the coast of England, from just southwest of Lyme Regis. We actually scanned it in the field, and it's available on the NHM Sketchfab website if you want to go and have a look at this. It's a 3D model. We can't show the 3D here, but it's actually in 3D. And we can see the rock record through one of these warming events. So around this time, we know from the plants, from the stomata of the ginkgos and other plant relatives, that CO2 levels went up from about 750 parts per million in the late Triassic to about 1,500, 2,000 parts per million in the earliest Jurassic, and that's associated with, say, one of these big 5 mass extinction events. And if we zoom in on the rocks, we can actually see what happened, what the seafloor looked like at that time as these sea levels went, as CO2 levels went up. So if you look at the bottom part of the screen here, you can see the rocks are sort of generally quite sort of bubbly looking. They look quite sort of, they're paler, and they look a little sort of lumpy. And that's because the seafloor there is full of burrows. Animals who are living there, they're burrowing into the seafloor. There's a lot of oxygen around. It's quite a normal marine setting. Just above that is this period of peak CO2, about 2,000 ppm, as I mentioned. And hopefully you can see there that the rocks are very different, and you can see hopefully sort of thin horizontal lines on the rocks there. And there's darker coloured as well. And we call those laminations, those thin lines. And to get those preserved in seafloor sediments, which these are, the only way you can get those preserved is if there's no animals burrowing into the seafloor. So we've sort of lost all the animals that lived on the seafloor burrowing away. And why is that? It's because as you warm the oceans, as you warm water in general, you have less dissolved oxygen in the water for the animals which live there to use. So if you don't have enough oxygen, you can't support a population of animals in the sea or on the sea floor. And so you get this record of these laminated mudstones in this case, which we would call a dead zone. And biologists at the present day are worried because we might get these dead zones in the future as we continue to warm the planet. Because what is the same for the present day, warm water holds less oxygen, is the same 200 million years ago. It's a physical fact, it's chemistry, and will be the same in the future as well. So if we warm the seas, they will hold less dissolved oxygen, and there'll become a point, certainly in areas of the seafloor where essentially it'll be dead zones. There won't be enough oxygen to support life.
And what does the fossil record tell us about how animal life in the ocean responded during these sorts of events?
Yeah, so that's actually one of the great things about the fossil record is that not only do we see what normal marine communities were like before these warming events, we can actually see what they were like peak warming, as we've just seen there, with these expanding dead zones. But also we can see how the ocean system then recovers as carbon dioxide levels come down again and the world cools. So yeah, the fossil record is great because we can see all of that process preserved time and time again through these different events in the rock record.
Brilliant. And there's one slightly unusual, I think, for many people watching, impact on animal life. I know that you study in the oceans, and that's animals getting smaller. Tell us about this.
Yeah, so this is a prediction that many of the marine biologists are making for the future as we warm the oceans. Although, as it said, oxygen levels will drop, so there'll be less oxygen in the water. But actually, as we know from a sort of very basic chemistry again that you and I would have done at school, if you heat up chemical reactions, they go faster. And that's the same with the reactions in our bodies or in organisms' bodies, so the metabolism. So as you warm up the waters, metabolism increases, animals need more oxygen, but there's less around. So one of the ways that they can cope with that is actually to become smaller. And smaller animals generally are more efficient at using oxygen. And also there might be impacts such as ocean acidification or impacts on productivity and food supply, which also will generally lead to animals becoming smaller. So shrinking is a key prediction for future warming. As we warm the oceans, organisms will become smaller, is the prediction. Well, we can test that from the rock record because we can go back to these past events and we can measure the sizes of the fossils, the animals that were living at the time, and see how, test this prediction, see whether it comes true or not. And here's one of our former students, David, who's measuring here some sea urchins. And this is from one of these warming events that actually happened within the chalk seas. So when you look at the White Cliffs of Dover and around the south of England, there's an event about 94 million years ago in there, which is one of these big warming events again that led to sea level rise and extinction of marine organisms. So he's looking at these sea urchins, measuring the sea urchins again from the collections in the museum, historic collections, to see what happened. And I think there's a sort of cartoon summary that David put together of all his thousands of measurements that he made. So here, if you like, is a snapshot picture of the seafloor back in the Cretaceous there, in the late Cretaceous. The panel at the bottom shows the normal sea urchin community and a normal sort of pre-event times. And the panel above shows the warmest seas in what's called the Turonian stage of the late Cretaceous. And there are some of those, there are about 3 of those different sea urchin groups you can see become smaller. So there's the purple one and the red one sort of in the middle. And then off to one side is one that's actually buried deeply within the sediment. So there are sea urchins that actually burrow, and these are really important for productivity. And those ones become really small during this event. The other groups there either don't really change too much or actually become a little bit bigger. And the reason for that is that we think is that perhaps these ones ecologically are doing something a bit different to the other ones. And possibly actually they're responding a bit more to the additional food supply that's around at the time. So certainly some groups were probably a bit more resistant to this effect, but certainly we do see shrinking in this particular example in several of these echinoid sea urchin groups.
And this shrinking is something we see time and time again in different extinction events. Is that right?
Yep. So again, it doesn't matter what species you look at. It doesn't matter which event you look at, how fast climate change was or how big climate change was. We can see this time and time again in a lot of these marine groups. So there are always exceptions every now and again, but mostly yes. So we see a shrinking in the fossils at the times of past warming, which supports this prediction for the future that animals within our seas are going to become smaller if we continue to warm the planet as we're doing.
And it's fascinating how much we can learn about our past climate just from the fossil record. But why is this information important today? Why should we care about shrinking echinoderms?
Yeah, it's about what's going to happen to the ocean. So biologists and ecologists at the present day can only make predictions for the future. And of course, we can test this from the fossil record, so we can know whether these predictions are likely to happen or not. And the shrinking one is one that we see lots of evidence for. Why is this important? Well, I don't know about you, Alison, but I quite like fish and chips personally, and it is lunchtime, and I am getting a bit hungry. But this prediction is not just about sea urchins or other organisms within the sea. This is actually impacts directly our economy, our society, the animals that actually we rely on for food. And it's not just the fish, but it's also the shellfish, of course, within marine ecosystems as well. And fresh water. This is not just related to the sea. This is also holds the same for freshwater, all aquatic animals, if you warm their environment up. So the prediction is that we'll see shrinking. The outcome for you and me on a daily basis, if this happens over the next few decades, is that we're going to see smaller portions, and that, of course, has a knock-on effect on economy and on society. If actually this main food source that we all use around the world is not going to be as good as it was.
And of course, there are other wider impacts as well, all kinds of impacts of climate change. And some of the data from the fossil record it's a little bit scary. I mean, we've spoken about dead zones, mass extinction events. Some of us may be suffering from eco-anxiety. How do you react to some of these findings from the fossil record?
Yeah, I think there's two things here. One is that the fossil record shows us how bad things can be as we warm the planet, and a lot of these events are actually, the warming is much higher than the present day, even for the end of this century. But of course, if we did nothing, we would eventually get to these sort of levels. But there is a good news story actually out there for the fossil record, that even with these big events that have happened in the past, life on Earth and life in the oceans has recovered afterwards. So even though it does get quite bad at the time, actually life on Earth is pretty resilient to these warming events. So in terms of the current problems and the current climate emergency, it's really about us, and it's about the impacts on our society, our way of living, that we really need to worry about. I think we need to worry about less on the whole planet, because actually eventually that will recover, and life is resilient to these big events. So it's a message, I think, that's sort of there's two parts to this. One is the impact on us and human society, which I think is very real, because as a species we have never been through one of these big warming events before. But some groups, especially in the oceans, and actually on land as well, have been through these crises before. And I think life, in terms, the opposite to extinction, if you like, is origination, and new animals and plants will evolve to replace those that will become extinct.
Absolutely, and to me that is a hopeful message. The planet is resilient. What we do makes a difference. We can make changes, and the planet can recover. Unfortunately, we are out of time, Richard. It has been fantastic chatting to you today and finding out about your brilliant research. There's so much more on our museum website, isn't there? If people are interested in what we've talked about today, there are lots of articles, lots of information on our museum website. You can find out more about Richard's work. You can find out more about our museum science and work generally related to the Anthropocene, and find out more about climate change as well. So do check out those website resources. Richard, we have to say goodbye to you for now. It's been brilliant. Thank you so much for chatting, and hopefully we can chat to you again soon.
Yeah, thanks, Alison, and thanks everyone.
And thank you to you, our viewers, for joining us today, for your questions and comments. Apologies if we didn't get to everybody's questions, but thank you so much for joining us. I hope you enjoyed that as much as I did. Do join us again next week. We're going to be finding out what role fish can play in capturing carbon in our oceans. Don't miss that one. Until next time, take care. We hope to see you then.